If you shine a dim blue light on a metal plate, electrons can fly out instantly, but a blazing red light won't knock out a single one. That sentence should feel wrong, not mysterious, not quantum, just wrong. Because in your everyday life, if you want more effect, you add more energy. You turn the knob up, you crank the brightness, you wait longer. That's how everything works. A tiny stream can fill a bucket if you give it enough time. A weak push can move a heavy box if you keep pushing. So if light is delivering energy to electrons, why doesn't a super bright red light eventually build up enough energy to kick them out? And why does a faint blue light succeed immediately? Most of us hear the standard answer, photons, little packets. Each photon has energy proportional to frequency. Blue photons are energetic, red photons are lazy. End of story. But if you've ever heard that explanation and still felt like you didn't actually understand what was going on, you're not alone. Because that explanation is correct, but it can leave a hole where the real understanding should be. Here's the missing piece. The photoelectric effect is not primarily telling you what light is. It's telling you something about how energy can and cannot be transferred to matter. It's a story about a rule in nature. When an electron absorbs energy from light, the energy does not dribble in. It does not arrive as a slow trickle. It arrives in a single, indivisible transaction. And once you see that, the entire effect becomes inevitable. Not weird, inevitable. So let's do it the Feynman way. Let's not start with the fancy words. Let's start with the crime scene, the raw experimental facts. Imagine you have a clean metal surface in a vacuum. You shine light on it. You connect it in a circuit so you can detect if electrons are leaving. When electrons pop out, you can measure a current. You can also measure how fast those electrons are going by applying a voltage that tries to stop them, like an electric hill they have to climb. The bigger the stopping voltage, the more energetic the electrons must have been when they escaped. Now here's what the experiment tells you, and these are not subtle details. They are blunt, stubborn facts. First, for any given metal, there is a minimum frequency of light below which no electrons come out. It does not matter how bright the light is. It does not matter how long you wait. Below that frequency, nothing. Silence. Second, above that threshold frequency, electrons come out essentially immediately. You don't need to shine the light for minutes or hours while the electrons charge up. If the light is of high enough frequency, the electrons start flying out without measurable delay, even when the intensity is very low. Third, if you increase the intensity while keeping the frequency fixed above threshold, you get more electrons. The current goes up, but the maximum kinetic energy of the electrons does not increase. In other words, brighter light ejects more electrons, but not faster electrons. Fourth, if you keep the intensity fixed and increase the frequency, the electrons come out with more kinetic energy. Their maximum kinetic energy increases linearly with frequency. So we have three control knobs: intensity, frequency, and time. And the universe responds in a pattern that seems almost designed to annoy classical physics. Because if light were just a wave carrying energy smoothly, the natural expectation would be different. Brighter light should deliver more energy per second. So even if the frequency is low, a very intense wave should eventually deliver enough energy to an electron to knock it out, maybe after a delay. And if you make it brighter, the electrons should come out with higher energy because you're delivering more energy. But the experiment refuses. So the question becomes, what exactly is the classical picture predicting, and why does it fail? Let's give classical physics its best shot. Don't caricature it. Classical physics is not stupid. It's brilliantly successful. So if it fails here, it must be failing for a deep reason. In the classical view, light is an electromagnetic wave. It's a wave of electric and magnetic fields that oscillate in space. When that wave hits a metal, the oscillating electric field pushes on the electrons in the metal back and forth, like shaking a bunch of tiny charges. That part is perfectly reasonable. An oscillating electric field exerts a force on a charge, so the electrons jiggle, they accelerate. And whenever charges accelerate, they can absorb or emit energy. That's also classical. Now, what happens if the light is dim? Dim means the amplitude of the electric field is small. The push is gentle. So the electrons jiggle weakly. They gain energy slowly. If the light is bright, the amplitude is larger. The push is stronger. The electrons jiggle more vigorously. They gain energy faster. This suggests a picture like charging a capacitor. The electron is being driven by the wave, and it is gradually picking up energy from it. If the electron needs a certain amount of energy to escape the metal, like climbing out of an energy well, then brighter light should get it out sooner, and intense light should always be able to get it out eventually. And crucially, even if the frequency is low, classical physics would say that shouldn't matter as much as intensity, because what matters is how much energy you deliver, not the color of the wave. Frequency changes the rate of oscillation, but if you make the wave strong enough, you can deliver lots of energy. So classical physics predicts no threshold frequency, or at least not a sharp one. It predicts a time delay for low intensity, because you need time to accumulate energy. It predicts that electron energy should increase with intensity, because more energy in the wave means more energy available to give to electrons. All wrong. So where does classical thinking go off the rails? Here is the key. Classical waves spread energy out over space and time. They do not naturally concentrate energy into one tiny spot unless you do something special, like focus with a lens or cause interference patterns. But even then, the energy is still spread out over some region. An electron, however, is a tiny object. It needs a certain amount of energy concentrated into it, and concentrated quickly, in order to escape. It needs the escape energy in one go, not as an IOU, and that is the real crime scene. That's where the mystery lives. How does a wave, which distributes energy continuously, deliver enough energy to a single electron essentially instantaneously, especially when the light is very dim? Let's make that problem vivid. Picture a dim light shining on the metal. Dim means that the energy arriving per second per square centimeter is small. The energy is not concentrated, it's spread over a whole area and over time. Now the metal has an enormous number of electrons near the surface, billions upon billions. The incoming energy from the wave is spread across those electrons, it seems, because the wave is interacting with the whole surface. If classical physics is right, each electron should receive a tiny share of the wave's energy, just a little nudge each cycle. Then gradually, over many cycles, maybe one electron accumulates enough energy to escape. But that accumulation idea already hides a problem, because energy in classical physics is not tagged with a name. It does not belong to one electron forever. Electrons are colliding with each other constantly inside the metal. They are interacting with the lattice of atoms. Any energy one electron gains is quickly shared, redistributed, lost as heat. It is extremely hard for a single electron to hoard energy in a metal the way a battery hoards energy in a capacitor. Metals are good conductors. That's what they do. They share. So if energy is arriving in a slow trickle and is constantly being redistributed among many electrons, it should be very hard for one electron to reach the escape threshold. You would expect a long delay. You would expect the whole surface to warm up first, and only then maybe electrons start leaking out because thermal agitation becomes strong enough. But that's not what happens. Instead, the moment the light frequency is high enough, electrons come out immediately, even with very low intensity. That means the energy transfer to an electron is rapid and localized. So here's a way to say it. The photoelectric effect is evidence that an electron does not absorb energy from light continuously, the way a classical oscillator absorbs energy from a driving force. It absorbs energy in a discrete event. And once you accept that, a threshold makes sense, because if the energy arrives in one package, either that package is big enough to pay the escape cost or it isn't. You can't pay half a toll today and half tomorrow if the toll booth doesn't accept partial payments. Let's talk about that toll booth, because that is one of the cleanest ways to build intuition without lying. The surface of the metal is not a free place for electrons. Inside the metal, electrons can roam relatively freely among the atoms, but at the surface there is an energy barrier. It's like a cliff edge. The electron is bound to the metal by electromagnetic forces. To leave, it must do work against those forces. That minimum required energy is called the work function. The work function is not the energy of an individual electron, like this electron is worth 4 electron volts. It's the energy cost to pull an electron out of that particular metal surface. It depends on the material and on the surface condition. Now imagine a toll gate that charges exactly $4 to pass. You can't pay with $3 and promise the last dollar later. The gate doesn't open until the full amount is paid. That's the work function. So now we ask, how is the toll paid? How does light supply that energy? If energy transfer were continuous, you could picture the electron gradually saving up pennies from the wave until it reaches $4. But the experiment tells you that doesn't happen in any measurable time. Even with dim light, electrons come out right away, as long as the frequency is above threshold. That suggests the toll is paid in a single payment. And that is the heart of Einstein's idea. Not that light is made of particles in the ordinary sense, but that when light exchanges energy with matter, it does so in chunks proportional to frequency. In modern language, we say a photon of frequency f carries energy hf. The electron absorbs one photon. It receives hf in one shot. It must use f, the work function, to escape. Whatever is left becomes kinetic energy, k is hf. Now you can see the threshold frequency. If hf is smaller than f, there is no leftover energy to become kinetic. In fact, there is not even enough to escape, so no electrons are emitted. And intensity becomes something different. Intensity in this story is not each photon becomes more energetic. Frequency controls photon energy. Intensity controls how many photons arrive per second. So brighter light means more photons per second. That means more electrons can absorb photons and get emitted, so current increases. But if the frequency is fixed, each photon has the same energy Hams. F, so the maximum kinetic energy stays the same, exactly what the experiment shows. And time delay disappears because absorption is not a slow accumulation, it's a single event. If a photon arrives and is absorbed by an electron near the surface, that electron immediately either has enough energy to escape or it doesn't. The clock doesn't matter. The electron doesn't need to wait. Now you might think, okay, fine, photons. But isn't that just swapping one mystery for another? Why should energy exchange be quantized? Why can't an electron absorb energy gradually from the wave? Excellent. That question is exactly the one that makes the photoelectric effect more than a historical footnote. Because if you just memorize photons, you miss the real intellectual leap. The universe is enforcing a rule about energy transfer at small scales. So let's dig into why the gradual absorption idea is not only contradicted by experiment, but also conceptually unstable. Imagine light as a wave spreading out. The energy in that wave is distributed across the wavefront. If the wave is dim enough, you can think of the energy density being extremely small. Classical physics says energy can be divided arbitrarily. You can make it as small as you like. You can have a wave carrying 1/1,000,000th of a joule or 1/1,000,000th, and it's still a wave. Now suppose that wave interacts with an electron. If energy transfer is continuous, then the electron might absorb an extremely tiny amount of energy at each instant. But then you run into a strange question. What is the smallest possible energy transfer? Classical physics says there is no smallest. It can be arbitrarily small. But matter doesn't behave that way. Matter has quantized energy states. Even if we don't fully explain band structure, we can say something fundamental. Electrons in atoms and solids occupy allowed states. They don't slide smoothly through a continuum of energies like a classical marble rolling down a hill. They have specific energy levels or bands. This means the electron cannot absorb just any random amount of energy and remain in a physically allowed state. The electron has to end up somewhere allowed. Now, in a metal, the situation is more complex than in an isolated atom. But the key idea remains. The electron's ability to absorb energy is tied to quantum rules. Those rules can allow certain transitions and forbid others, and they lead to discrete exchanges. So a continuous wave picture on its own doesn't match the discrete behavior of matter. The photoelectric effect is one of the first places where you can see that clash in a brutally simple way. It's not that classical waves are wrong as waves. Waves still explain interference, diffraction, polarization, all of that. But the classical wave description fails when you ask, how does the wave deliver energy to individual electrons? And this is the unique framing. Light can behave as a wave in propagation, but energy exchange happens in quantized events. Those are not the same question. You can have a wave that is spread out, but when it interacts in chunks. This is not an optio. Null philosophical interpretation. It is enforced by the data. Let's return to the stopping voltage measurement because it's one of the cleanest pieces of evidence. Imagine you build a circuit where emitted electrons have to travel to a collecting plate. You apply a voltage that repels electrons, like building an electric hill they must climb. If the voltage is too high, the electrons can't make it. The current stops. The voltage at which the current just drops to zero is called the stopping potential. Now, the stopping potential tells you the maximum kinetic energy of the electrons. K max equals EV stop. When you measure V stop for different light frequencies, you find a straight line relationship. Higher frequency gives higher stopping voltage, and the slope of that line corresponds to Planck's constant h. That's astonishing, because Planck's constant originally appeared in blackbody radiation and seemed like a mathematical trick. But here it appears again in a completely different phenomenon, as if nature is saying, no, this constant is not an artifact. It's a real conversion rate between frequency and energy. And the line does not start at zero. It crosses the frequency axis at a threshold frequency f0, and that threshold corresponds to fh, so K max equals hf if. This equation is not a philosophical statement. It is a direct summary of the experiment. It tells you there is a linear relationship between photon energy and electron kinetic energy with a fixed offset corresponding to the work function. That is the essence. Now, we should be careful about what this does and does not mean. It does not mean that every electron comes out with exactly that kinetic energy. In reality, electrons have a distribution of energies inside the metal. Some start deeper, some lose energy in collisions before escaping, so you get a spread. But the maximum energy is what follows the clean equation, because that corresponds to electrons that absorbed a photon and escaped with minimal losses. It also does not mean that light is always best imagined as little bullets traveling. In many cases, thinking of light as a wave is the most useful picture, but when it comes to energy transfer, the particle picture becomes necessary. Here's where the vending machine analogy can help. Imagine a vending machine that sells a snack for $4. It accepts only bills, not coins. You can insert one bill at a time. If you insert a $5 bill, the machine gives you the snack and returns $1 change. If you insert a $3 bill, nothing happens, no snack. And no amount of additional $3 bills, inserted one after the other, will help you if the machine doesn't add them up. Suppose the machine doesn't have memory. It either accepts a single valid payment or it doesn't. That's the photoelectric effect. Frequency sets the denomination of the bill. Intensity sets how many bills per second you try. Time only increases the number of attempts. It doesn't change the denomination. If your bills are too small, you can spam the machine for hours and you will never get a snack. If your bills are big enough, even one bill can work immediately. Now, of course, a R. EL vending machine can store money, but the point is, the electron metal system does not store partial photon payments in a way that allows accumulation across multiple low-energy photons. The absorbed energy either gets you over the barrier or it gets dissipated internally. And that brings us to another subtlety. What happens to photons below the threshold? Do they just bounce off? No, not necessarily. The metal can still absorb the light, heating up. The energy can still go into vibrations of the lattice, into other excitations, into heat. But it doesn't come out as photoelectrons, because it's not being delivered in the right kind of transaction to overcome the work function. So the statement red light doesn't eject electrons doesn't mean the red light has no effect. It means it can't perform that particular job. And here's another surprise. Even for the same frequency, not all metals behave the same way. Some metals have lower work functions, so they can emit electrons with lower frequency light. That's why alkali metals are often used in demonstrations. They have relatively low work functions, so visible light can trigger emission. This tells you the threshold is not a property of light alone. It's a property of light interacting with matter. It's about the barrier at the surface. So far, we've built a coherent story. Energy exchange is quantized, and that quantization depends on frequency, but there is still a big elephant in the room. If light is a wave, and the wave is spread out, how can it deliver a whole photon's worth of energy to one electron at one location? In other words, how can the wave be spread out and yet act like a concentrated packet in interaction? This is where the photoelectric effect becomes a doorway to the deeper quantum view. The photon is not a tiny marble traveling along a definite path in the naive sense. It is a quantum of the electromagnetic field. The field can be spread out like a wave, but the energy is quantized in units of hf. When the field interacts with an electron, the energy transfer happens in a discrete quantum, so you can have a wave-like probability amplitude for where the photon could be absorbed, but when it is absorbed as a whole. This is one of the central quantum ideas. A process can be spread out in possibility, but localized in outcome. And that's the new way to explain the photoelectric effect. It's not a story about light as a particle. It's a story about how quantum systems exchange energy. The wave description tells you about propagation and interference. The quantum description tells you about absorption and emission. Once you see that division of labor, the effect stops being a weird exception. It becomes a natural consequence of a deeper rule. Now let's revisit the three paradoxical facts and watch them fall into place. Why is there a threshold frequency? Because there is a minimum energy required to remove an electron from the metal. F. Since the energy comes in packets HF, you need HFF. That translates directly into FFH. Frequency is the gatekeeper because frequency sets packet size. Why is there no time delay? Because ine. RGI transfer is not gradual. If a photon is absorbed, the electron gets the energy in a single interaction. If it's enough, the electron escapes immediately. If it's not enough, the energy becomes internal excitations or heat. Waiting does not help because the system does not store partial photon payments in the right way. It dissipates them. Why does intensity affect the number of electrons but not their maximum energy? Because intensity changes the number of photons, not the energy per photon. More photons means more opportunities for absorption, hence more emitted electrons, hence higher current. But each photon has energy HF, so the maximum electron energy is determined by HFF, independent of how many photons you send. That is the entire structure. And here is the moment of synthesis. The photoelectric effect is not the discovery that light is made of particles. It is the discovery that energy exchange between light and matter is quantized, with the quantum size determined by frequency. That's the deeper statement. Now, this might leave you with a final question, and it's a good one. If intensity is the number of photons, why can't multiple low-frequency photons combine their energy to eject an electron? Why can't an electron absorb 2 red photons and equal 1 blue photon? Sometimes in other processes that can happen. Multi-photon absorption exists in modern optics, but the key is it requires special conditions and high intensities because the probability of absorbing 2 photons essentially simultaneously is low. In ordinary photoelectric experiments, the dominant process is single photon absorption, and the system dissipates energy quickly into the metal before another photon can add to it. So in the typical setup, you don't see accumulation from multiple low-energy photons because the electron-metal system has a very short memory. Any energy absorbed below the threshold is quickly shared and thermalized. It doesn't stay available as a stored chunk in one electron. So the rule is not it's impossible for 2 photons to help. The rule is, under ordinary conditions, the photoelectric effect is dominated by single photon events, and below threshold frequency, single photons can't supply enough energy to escape. This is another Feynman lesson. Don't turn a simplified model into a metaphysical law. Nature is subtler. The simple model explains the main effect, and then you refine it when you look at more specialized phenomena. Now step back and notice what we've actually learned. We started with a paradox. Dim blue works, bright red doesn't. We tried to explain it with classical waves and got stuck because waves smear energy out and metals redistribute energy too quickly. We introduced the idea of a surface barrier, the work function, and realized the electron needs a minimum payment to escape. We discovered that the payment comes in indivisible chunks proportional to frequency, which makes frequency a gatekeeper and intensity a rate control. And then we realized the deeper philosophical point. Light can propagate as a wave, yet exchange energy as quanta. That is no contradiction. It's a clue about the quantum structure of fields and matter. So the title, "No One Explains the Photoelectric Effect This Way," gets its payoff here. The photoelectric effect is best understood as a rule about transactions. You can picture the metal surface as a gate with a fixed price. You can picture light as a stream of offers. Each offer has a size determined by frequency. If the offer is big enough, the electron can pay the toll and escape instantly. If not, the offer is wasted into heat, and no amount of waiting changes the size of the offer. And the universe insists on that single payment rule. Now, if you want to carry this understanding forward into the rest of quantum physics, here's the lens that matters. Quantum mechanics is not primarily about particles being weird. It's about the quantization of certain properties, energy, momentum, angular momentum, and about how those quantized properties are exchanged in interactions. The photoelectric effect is one of the simplest windows into that. It tells you energy is not infinitely divisible in every context. There are minimum chunks, and those chunks depend on the frequency of the electromagnetic field. And here's what still feels like a magic trick, even when you understand it. You can spread the light out as a wave, and it will still deliver its energy in lumps when it interacts. It's like having a mist that forms raindrops only when it hits a leaf. The mist can be continuous in the air, but the delivery is discrete at the moment of contact. That's the quantum world: continuity in propagation, discreteness in interaction. So the next time you hear photons or particles, you can nod, but you can also say something sharper. Photons are the quanta of the electromagnetic field, and the photoelectric effect is the proof that energy transfer between light and electrons happens in indivisible packets whose size is set by frequency. And once you see it as a transaction problem, the paradox stops being a paradox. It becomes a lesson